He was instrumental in the Deep Stack team. That was the first program to beat professional players at Heads Up No Limit Poker, and has gone on to explore more ideas in how we can understand how we interact with other agents. And this is some ongoing work in that direction. Take it away, Dustin.
Great, thanks, Mike. Yeah, thanks everyone for being here. Thanks for having me. So this is my talk on efficient deviation types and learning in extensive form games. This is from a paper that appeared at ICML last week, and it's joint work with Ryan D'Orazio, Mark Langtow, James Wright, and my co-supervisors, Michael Bowling and Amii Greenwald. All right, and the goal of this work is more effective algorithms for playing multiplayer general sum extensive form games. That is, we want algorithms for navigating complicated multi-agent environments where there's sequential decision making, and where all those agents might have incentives that are not entirely aligned with our own. And so we start working on this from an online learning perspective. So there's going to be a learner, that's going to be the algorithm, that's going to be the agent that our algorithms are going to be controlling. This learner is going to interact with the world by producing strategies represented by pi I t here. That strategy is going to get played out in the world where there might be other agents also making their own decisions. Ultimately, though, the learner isn't going to reason explicitly about what the other players are doing, but instead is going to just observe a payoff function that the environment gives back to the learner that encapsulates the decisions that the other players made and lets the learner learn from the different things that the learner could have done in order to improve their strategy on the next round. So after they produce a strategy, they're going to get a payoff function. They're going to use that to improve their strategy, and they're going to continue living their life like this. So over the course of the learner's lifetime, they're going to accumulate some average payoff seen here. And the way we're going to evaluate whether or not the learner is doing a good job is to consider a deviation. Here, a deviation is going to be a function phi that maps strategies to other strategies. So if we apply that function to every strategy that the player produced over its lifetime, that's going to give us a new sequence of behavior that the learner could have done instead. And that's going to have its own average payoff, given the functions that the learner observed. And so that's this value here. And then the objective for the learner is going to be to accumulate enough reward to do nearly as well, or at least as well, as any deviation from some fixed set of deviations, capital phi, over their entire lifetime. And so we call this objective hindsight rationality, because we're looking out over, in hindsight, over the learner's lifetime and checking whether or not they could have done better than if they had done something else. Now, another way this objective, and an equivalent way this objective is often framed, is that the difference between these two sums will be taken, and we'll call that regret. And then hindsight rationality here is the same as minimizing regret and making sure that it grows sublinearly over time. All right, so then in this framework, the problem of designing algorithms is largely a problem of making use of structure within the deviation set and within the environment to come up with efficient algorithms for achieving this goal. So now I'm going to talk about the structure of the environments that we're thinking of. So here, I'm going to talk about extensive form games. Extensive form games are a model of sequential decision making where every agent, every player in this game takes turns taking actions, and every action is recorded in the game's history. Every action is recorded in the game's history. So the set of all these histories come together to form a tree, and that determines every possible way this game could play out. So for example, in this game that I'm showing here, player 1 acts first, and then player 2, and then player 1 acts again, and then there's a chance outcome that could be the roll of a die. And at the end of the game, we reach these terminal histories, one of these terminal histories. And at any terminal history, all the players receive their payoffs, depending upon the rules of the game. Now, we want to be able to represent games where players may not observe every action that every other player does. So to do this, we introduce the idea of information sets. This is where we group histories together, and players are only able to act knowing that they're in a particular information set, not knowing that they're in any given history. So the way I've drawn it here, we've grouped together the two histories where player 2 acts. So they don't get to observe whether or not player 1 chose left or right at the beginning of the game. Effectively, player 1 and player 2 in this game act simultaneously at the beginning of the game. Now, this game tree view of extensive form games is nice to describe all the ways a game could play out from an outside perspective, but it's not going to be as useful for us in describing how algorithms, learning algorithms work that are trying to ensure hindsight rationality. So instead, we're going to have a representation for what a particular player's perspective of the game is. And we do this just by pulling out all the information sets for a given player and joining those together in trees. So for example, here, if we take out the information sets from player 1 and build a tree out of them, we can see that player 1's perspective of this game is that they take an action at the beginning of the game. Then there's some outcome determined by external factors. And then player 1 acts again. And then one of 3 outcomes occur where they get some utility according to the utility function U1. On player 2's side, we can see that player 2 just takes one action. They see some other observation, and they end up receiving some payoff at the end of the game. All right, so we're going to make use of this kind of information set tree representation of the game from here on out. Okay, so now that we've seen what games look like, what do strategies look like in these games? So here's another arbitrary game for some arbitrary player I. And a strategy in an extensive form game is an assignment of behavior to every information set. So for example, here's what the always left strategy looks like in this game. Just that every information set, we assign probability 1 to the left action, and we'll always end up at the left, left, left outcome and get the utility there. Notice that even in this small game, we have 5 information sets with 2 actions, and also, therefore, we have 2 to the 5 or 32 different strategies, just every different combination of the way the actions could be assigned. So notice that this is exponential in the number of information sets we have. So the set of strategies grows very quickly with the size of the game. Now, another way to represent strategies that's slightly more compact is we can avoid defining the behavior at information sets that are never reached, like these 2. And strategies like this are called reduce strategies because they remove this extra information. All right, so now what do deviations look like in these settings? So if we have a strategy like the always left strategy here, and we apply some deviation function phi, we're going to get out some new strategy, maybe the one that plays left, left, right, right. And notice here that even in a small game, there are at least 32 different ways to transform any given strategy, and 32 to the 32 possible deviation functions, right? Total mappings from the set of strategies to strategies. So what this means, so this is doubly exponential in the number of information sets. So it's not going to be feasible to work with the full set of deviation functions and ensure hindsight rationality with respect to that set. Instead, we're going to need to restrict the set of deviation functions that we're looking at to a smaller, a less complicated set. And the way we're going to do that is by enforcing that our deviations need to conform to the information structure of the extensive form game. where information can only flow from the start of the game to the end. So deviations like this were described by von Stengel and Forge as being procedurally generated through the actions of a fictional deviation player. So this deviation player gets to see the parts of the input strategy and then makes their own decisions for player I. So I'll show how this works with an example. So we start at the beginning of the game. We're transforming the strategy pi I according to this deviation function phi. And we see in this first information set that the input strategy plays action 3. So that's that action. Now the deviation player, knowing this information, gets to choose a new action to play. So perhaps they choose action 1. So they're taking action 1, transforming it to action 3, like that. So that's the first transformation this deviation player is going to do. In the next information set, the deviation player gets to remember that the input strategy played action 3 in the previous information set. They also get to see at this information set that the input strategy would play action 1. And again, they need to play some other action. So perhaps this time the deviation player doesn't modify the action at all. It just plays action 1 as well. In the next information set, again, the deviation player gets to remember what they saw before. And also they get to remember the input action from the previous information set. Again, they see the input action and they have to make a choice. So this time they change action 2 to action 1. So notice then that the deviation player's behavior can only depend on their observations earlier in the game, which rules out deviation functions of the form that change the part of the strategy at the beginning of the game based on what that strategy does at the end of the game. So this rules out a bunch of those functions. However, notice that the deviation player's memory, represented by this string, grows linearly, which means the number of different configurations that string can take on, the number of memory states, grows exponentially with depth, which also means that the number of deviations grows exponentially in depth. So this set as well, although it's less complicated than the full set of deviations, is still going to be too complicated if our game has any depth at all. One way to avoid this, and this was described by von Stengel and Forge and has been used in many papers since, is just to assume that the strategies you're going to transform are reduced. And I'll show how this reduces the complexity of this deviation set. So if we have some reduced strategy pi I bar, that takes the same action as the strategy before, action 3. This deviation function phi, again, is going to transform action 3 to action 1. But now we're at a new information set where a reduced strategy doesn't actually define any behavior. So in its place, we use this star character to denote the fact that the deviation player doesn't actually get any new information at this information set. And so they only get to work off of what was in their memory state before reaching this new information set. And so now they have to choose a transformation that just blindly chooses one action. So here, maybe they choose action 1. At the next information set again, they carry over what little information they have. And again, they have to make a decision. And maybe they choose action 1. But notice now the number of configurations of this memory state string grows only linearly, which means the number of deviation functions that you can actually represent here only grows linearly with depth as well. So this is how people have made these deviation functions efficient to deal with in the past. What this work, at least the first contribution of this work, is to take this idea of hiding information from the deviation player in order to come up with a set of deviations that are efficient to deal with in an algorithmic way, is to generalize that mechanism. Rather than imposing it on the types of strategies we're transforming, we're going to move that into the definition of the deviation itself. And we're going to be able to choose different places in the game where we either hide or give the deviation player memory. And that's going to result in strategically different classes, types of deviations. Okay, so now I'm going to describe behavioral deviations. That's our name for this general formalization of von Stengel and Forge's deviations. And the way they're defined is by imposing a particular action transformation at every information set and every memory state that we could have in that information set. So notice that these transformations are over the set of actions, not the set of strategies, but in aggregate, altogether, they form a transformation, a deviation over entire strategy spaces. All right, so I'm going to show how this looks in an example. So here we're going to build up a behavioral deviation phi by looking at what choices we could make at information sets going through the game. So at the beginning of the game, at this information set I0, there's only one memory state because the deviation player hasn't seen anything yet. So we could assign the internal transformation that takes action 3 and transforms it to action 1, otherwise leaving the behavior at this information set the same as it was from the input strategy. Okay, so that's one assignment that we can make to this information set. If we make that choice, now at the next information set, I1, there's going to be two different memory states that we could be in at that same information set, because we could reach information set I1 under this internal transformation if either the input strategy played action 1 or the input strategy played action 3. So that's going to correspond to these two different paths here. So under these two different paths, we can assign two different action transformations. So here we have the internal transformation from action 1 to action 2 that we see on the left. And on the right here, we have the external transformation or constant transformation that always plays action 1. And that's this transformation on the right. Now at the next, in the next level, on the left, we can see that again, we split the number of memory states that we could have at the next information set because there are different ways that we could reach that information set. But on the right, since every input strategy will always have their action at information set I1 transformed to the first action, we're always going to reach information set I3. And so we don't get any information about what the input strategy pi I at information set I1 was. So there's only going to be one other memory state there, and it's this 3-star memory state. So here, notice that we've hidden information from the deviation player at this information set. And then at I3, we can allow the deviation player to see what pi I at I3 would be in order to make their decisions going forward. So this is how this differs from what von Stengel and Forge described, where they had to restrict their strategies to be reduced. They wouldn't be able to represent the fact that the deviation player could see the strategy at information set I3. And so we represent, so this is, like I said, a behavioral deviation. We write the whole set of behavioral deviations in math like this, and we're going to use this pictogram like this to represent the set of deviations in a more intuitive way. Okay, so with that described, we can then start to take a look at the larger deviation set landscape within extensive form games. I know this slide is really busy, but I'm going to go through it a piece at a time. So at the top of the figure, we have the internal transformations that represent all the different transformations that you could do from one strategy to another. At the bottom, we have the external deviations that transform every strategy into one particular strategy. And these form kind of opposite ends of a spectrum of strength. So we have deviation classes that are strong at the root of these arrows, and we have weaker ones at the sink. So we've just described these behavioral deviations that kind of serve as a nice natural proxy for the internal deviations in extensive form games, because we've enforced this information structure. They're still going to be too difficult to deal with in most games, but we'll get there. Now, there's a set of deviations at the bottom of this figure where we already had efficient algorithms for dealing with those deviation types. So already efficient. One thing to notice about this set of deviations is that there was no set of deviations that were both efficient and captured all of the relevant strategic information. So for example, this top row of deviations, they're all distinct. None of them subsume each other. And so we're able to change that actually with these new, this set of deviations at the top of the figure are what we're calling partial sequence deviations. So these are new classes of deviations that subsume all of the previously defined ones, and where we actually have an efficient algorithm for ensuring hindsight rationality with respect to them. And so the algorithm that does that is going to be the subject of the next part of the talk. Okay, so I'm going to now talk about our new algorithm called extensive form regret minimization, or EFR. So EFR works by learning these immediate strategies at every information set I over time. And in order to do that, it asks a question, namely, how much incentive does the deviation player have to employ transformations at I, given that the deviation player follows some deviation phi to reach this information set, and also given that it plays the previous strategy pi I t for the rest of the game going forward. So the first, there are two sub-questions that need to be answered in order to answer this first question. One is, what is the value of every action under player I's current strategy pi I t? And then also, how often does every deviation that could reach this information set, how often does every deviation that could reach this information set reach it, and with what memory states? So the bottom question is answered pretty simply. It's just the counterfactual value of playing action A in information set I. And this is basically the expected payoff for playing action A, assuming that player I plays to reach information set I. So it's like a conditional action value. From the top of the tree, we need something a little bit more complicated. So we need to keep track of the memory probability. That is the chance that some deviation strategy, the deviation strategy that we get from applying deviation function phi to the learner's current strategy pi I t, the chance that it reaches information set I in a particular memory state G. So this is over all such deviations, all behavioral deviations, and all memory states that are realizable by those transformations. We look at this memory probability. So it's a value between 0 and 1, describing this chance. Now we can combine these two things to get an objective for learning the strategy at this information set. So in the brackets here, we have a difference of counterfactual value between the strategy that a deviation would use here compared with the value that the learner's strategy gets at this information set under the counterfactual value function. And this difference has been described before. It's called counterfactual regret, and it's been used in other algorithms like the counterfactual regret minimization algorithm. So we're going to be making use of it here. And then the other piece that we need, actually, I'm just going to simplify that to this phi notation, or this rho notation. And then the other piece that we need to do is to take into account the memory probability. So that's just going to weight this regret according to the chance that phi pi I t reaches this information set and memory state. So notice again that we're going to have one of these weighted regrets for every behavioral deviation. So we're going to have a bunch of these. And we want to ensure that all of these go to 0 on average over time. We don't want to have any regret under any of these behavioral deviations over time. So it turns out that this is actually a somewhat well-studied problem called time selection. So it's just the problem of minimizing regret with respect to a sequence of weighting functions, first described by Blum and Mansour. And so we can solve this just by using a modified no regret prediction with expert advice algorithm. And we give a really flexible version of regret matching in order to solve this problem. And I'm going to quickly go over what that algorithm looks like so you have a better idea of what kind of learning is going on. So we set the immediate strategy at information set I on the next round according to a 4-step procedure. So first, we accumulate all these weighted regrets over time. These are just the regrets that we saw before, but just summed over time. We take those cumulative regrets and we transform them into preferences according to some function f that I'll give examples for in a minute. Weighted, and so this is summed across all the memory states in the information set. So kind of giving an aggregate preference for one particular transformation. Then we average the transformations at this information set according to the preferences that we just computed. And then we set our strategy at this information set to be a fixed point of that average transformation. All right, and this algorithm is flexible because it permits the choice of link function f. So for example, so what we usually use in experiments is we take the max of 0 and the regret. So we just cut off the negative bits. Or another link function that's common in the literature is the exponential function. And this gives you the best regret rate in terms of the dependence on the actions. But the max one typically has better practical performance. Another thing this allows is that you can approximate the cumulative regrets instead of storing them all in a big table. So this is a problem if your game is really big. You can also predict the next instantaneous regret for every transformation. And this can give you some better performance if the environment is kind of regular in some different senses. Okay, so that's the algorithm. Now I want to say one quick thing about the magic of this kind of algorithm. And it turns out that even though EFR is only learning locally at every information set, it turns out that because it's learning locally at every information set everywhere throughout the whole game, you can actually get a stronger result to say that regret over the entire strategy space is minimized. So EFR will minimize the immediate regret at every child here. It'll also minimize the regret at every parent, which will mean that the full set of 2-step regrets are also minimized. And this kind of decomposition extends all the way from the start of the game to the end and for every behavioral deviation. So even though we're doing this local learning, we get this global nice result. Now, one problem you may have noticed is that the way I described EFR before, we were working with the full set of behavioral deviations. And like we said, there's an exponential number of these in the depth of the game. So that's going to be a problem because we need to keep track of regrets, one regret for each of them. So that's not going to be feasible typically. But what we can do is actually, it's really simple. We can just restrict the deviation set that we allow EFR to use to be some subset here of the behavioral deviations to make sure that our algorithm is going to be efficient. And that also allows us to reproduce algorithms that have been previously described within this kind of CFR family. So if we take the counterfactual deviations that look like this, that are going to play to some particular part of the game and then use the learner's strategy afterwards, we end up with the CFR algorithm that's been really successful in playing large-scale poker games. If we take the informed causal deviations they're associated with extensive form correlated equilibria, they're kind of popular in the game theory literature, we get an algorithm that is essentially ICFR from a recent award-winning work at NeurIPS, I think from last year. If we use the action deviations so that they play to some particular part of the game, then they change the strategy just at that local information set and then use the strategy for the rest of the game, we get an algorithm that's similar to policy gradient policy iteration. So this is to make a connection to the RL literature. So policy gradient policy iteration, or PGPI, is essentially a dynamic programming version of policy gradient. And in experiments, we're going to be looking at a similar algorithm that's slightly stronger, but it's very close. And it's going to be labeled ACT-IN, just to let you know about that. Now we can also, as I mentioned before, we're excited about these partial sequence deviations that are both efficient and powerful. And so we can get new versions of new algorithms by instantiating EFR with these deviation types. So if we use the twice-informed partial sequence deviations, that's the strongest form of deviation that we described under the set of partial sequence deviations. We label it TIPS. And the important thing to notice to ensure efficiency is that the number of deviations and thus the number of regrets that we need to keep track of grows only linearly with the depth of the game and cubically with the number of actions. So that's a lot more favorable than the full set of behavioral deviations. There's another slightly weaker class of deviations called the causal partial sequence deviations. And this reduces the number of the dependence on the actions to quadratic. Again, the counterfactual partial sequence deviations reduce the dependence to quadratic as well. And the cheapest partial sequence deviation is the blind partial sequence deviations, where the dependence is linear on the number of actions. All right, so maybe I'll take a quick break just to see if there are any questions before I get to some experimental results. All right, if everyone's happy with that, I guess I'll move on. Okay, so here I'm going to show some learning curves that are kind of representative. We have a lot more in the paper, but they're representative at least of the trends that we saw. So we're going to have 4 different instances of EFR. As I said before, we're going to have this ACT-IN algorithm that's kind of a proxy for PGPI or a reinforcement learning kind of approach. We'll have the traditional CFR algorithm, and then we'll have our TIPS instantiation of EFR. It's kind of the strongest partial sequence deviation version. And then we're going to have this BHV instance, which is EFR instantiated with all the behavioral deviations. We're only going to be looking at games that are small enough where we can actually compute how have an algorithm that's hindsight rational for the behavioral deviations. So we can see how much of a gap there is between the TIPS algorithm and the BHV algorithm. And we're going to show these results in some small games from the OpenSpiel framework. The details of these games aren't going to matter too much, but I'll tell you the salient features. So we're going to have two different versions of Goofspiel. Excuse me. So Goofspiel is an imperfect information card game that's notably zero sum because you're scored on whether or not you win the game. But the important thing between these two different variants is that in one version we have 2 players, and in another version we'll have 3 players. And then the third game that we'll show is a small version. It's a game called Sheriff. It's a small version of the Sheriff of Nottingham board game, if you're familiar with that. So it's going to have 2 players, but notably it's non-zero sum. So this is going to provide a little more challenge, for traditional algorithms designed for zero sum, 2-player zero sum games. And we're going to show 2 different learning scenarios. One is where the learning algorithm is going to be playing against a sequence of strategies that are oblivious, but they're going to change over time. So they're non-stationary. It's a non-stationary sequence of strategies, but they're just not going to be reacting to the things that the learner does. So the results here, we have on the x-axis, we have the number of rounds that are played. On the y-axis, we have the average payoff that the learner achieved. In the first 2 games, this is between 0 and 100, just the win percentage. And in the third game, this is just the number of points that are scored in Sheriff. So you can see here that the stronger deviation types, in particular TIPS and BHV, typically perform the best, by a substantial margin. CFR is somewhat close, but there does seem to be a noticeable difference. And then the act-in algorithm typically performs quite poorly over the full run. And we see that generally, that it doesn't do a great job. All right, so that's the first learning scenario. In the second, we're going to have a setup where we have all the learning algorithms playing and learning against each other simultaneously. This is going to be a little bit more difficult to get a firm ordering of the algorithms, but it's going to be a little bit more of a realistic setting. So here we have all the learning algorithms playing against each other, again, over 1,000 rounds, and higher is better, average payoff again. So here the 3 stronger algorithms are a little bit closer. There's still a gap generally between BHV and CFR. CFR actually does a little bit better than TIPS in 3-player Goofspiel, but they're quite close. And then, in Sheriff, there's a small edge between the stronger deviation types and CFR. As well, again, the act-in algorithm just does quite poorly compared to the other deviation types. All right, so those are all the results that I have. Does that all make sense? I'll take another quick break to see if there are any questions. All right, so with that, I guess I'll move on to the conclusions. I'm actually finishing up a little early, it looks like, today. So some conclusions about this work: behavioral deviations, generalizing the ideas that von Stengel and Forge had, are natural and expressive in extensive form games. The algorithm EFR is hindsight rational for any given set of behavioral deviations, and the computation of EFR scales very closely with that set's complexity. The partial sequence deviations that we described as kind of an efficient proxy of the behavioral deviations are both efficient and powerful. And in practice, EFR with stronger deviation types tends to do better. So that's kind of validating all of this theoretical work. Some remaining open problems, in particular, stronger deviation types require more computation. So it'd be nice to avoid that. And stronger deviation types also kind of paradoxically lead to worse regret bounds with respect to weaker deviation types. So that should be something that we should be able to rectify because we assume or we suspect that competing with these stronger deviation types will allow the learner to do better, and therefore it should that learner should outcompete by a lot more these weaker deviation types. So some possible solutions for this. We can characterize the potential benefit of a stronger deviation type in a given game. That's maybe one route that would let you choose, given a particular game, you could design some deviation types that will work better without too much cost. Another thing that would be even better would be to automatically navigate these trade-offs using ideas from the fixed share forecaster and context tree weighting that deal with these large class of experts. Unfortunately, so I've done some work on this, and it doesn't look like this is going to be feasible. But another idea that looks a little more promising is to weight the deviation regrets to improve performance with respect to weaker deviation types. This doesn't avoid the computational problem of these strong deviation types, but at least we could address the second concern. All right, and that's everything for me. Thanks very much for listening. And yeah, I'd like to hear any questions or comments. Thanks. And we do have some time, so if anyone is unclear and wants to go back and see something, yeah, we have time for that.
Thanks, Dustin. I had a question, which I think you answered, but I want to make sure that I am understanding this. So this is only going to work against fixed opponents, right? If I have an opponent that's also learning over time, then does that mess up essentially the regrets?
No, actually. So that's kind of the goal of this framework, this hindsight rationality idea, is that the learner is going to be playing strategies and learning from the payoffs they receive, but the other players are actually free to change how their behavior arbitrarily. Now, we do have to be careful that it's not like the learner is going to converge to some optimal strategy against some particular, players' strategies for the other players. What we're searching to guarantee is kind of this lifetime performance guarantee, right? That over time, according to all of the, sorry about that. According to all of the decisions that all the behavior that the other players made that might be changing over time, we're going to ensure that we wouldn't have wanted to do something else in that same amount of time. So it's a different kind of optimality notion than something like Nash equilibrium, where we're going to find a strategy that we could deploy against any other strategy and it's going to do well. And it's not like an optimal best response strategy that we could deploy and it'll do as well as it could possibly do against some particular strategy. Instead, we're going to try to be robust with respect to the future strategies that the other players might use.
Okay, to say that back, to make sure what you're saying is over the history of what you've played, you don't have regret, essentially. But exactly. It could be that everybody gangs up on you in the future, and then then you just really have to change your strategy as a result. But over your lifetime of what you've seen, there's no guarantee about the future, only about the past.
Yeah, so I mean, this kind of result is kind of funny because it's making a statement about the past from the past, right? Like in the future, I will be able to look back and see that I would not have wanted to play something different, right? So if in fact in the future, a bunch of players gang up on me and cause me to do poorly, I'm going to need to adapt to that. I'm going to need to improve my strategy against that coalition. so that in the future, right, in the next few rounds, I'm still going to be able to look back and say I did as well as I could have done. But it's going to be compared to the other things I could have done, right? So if they gang up on me in a way that I could never have been prepared for, then this still says that I'm doing the best that I can, essentially.
Okay.
Yeah, and it's not going to be forward looking about preparing for what strategies the other players might use, but it is going to adapt. As soon as they change their strategies, I'm going to adapt to them and continue playing well.
Great, thanks. That helped clarify things for me.
Thanks.
We've got a question in the chat as well.
Yes. And thanks, Mike, for that comment. Yeah, the future will eventually be the past, so I have to act well now. Yeah. So Ryan asks, does the choice of link function matter when we compare the different types of deviations in practice? That's a good question. I actually didn't do any experiments with that. So one other nice thing that I actually skipped over really quickly, concerning specifically these two different link functions that I mentioned, is that this ReLU link function doesn't have any parameters. And so we can have a parameter-free learning algorithm. Doesn't depend on the scale of the rewards, doesn't depend on the number of rounds. And so it's really nice to deploy, and it performs well in practice. Whereas this exponential function has this learning rate or temperature parameter that needs to be set according to different parameters of the game, or there are different dynamic learning rate schedules you can use. But all these things are slightly more complicated. And so for that reason, I didn't actually compare what the performance was like under different link functions. We do know that the regret bounds will be better under the exponential function if you tune that learning rate properly. Yeah, whether or not, so it is true. How does it depend? I'm just thinking now about the bound. I'd have to double check whether or not the link function impacts the bound's dependence on the number of these weighting functions, or like the number of different deviations that reach this information set. I think it doesn't, but I would have to go through the analysis on that. That might be actually something that would be worth looking into. Yeah, because that might show that the bounds would have a logarithmic dependence on the number of weighting functions rather than just the square root, which is what this ReLU function has. That's something to look at. Definitely, it's something to try empirically, and I suspect that the ReLU function will still win empirically, but definitely something to look at. Thanks, Ryan.
I have a question, Dustin, around some future suggestions you gave at the end around weighting different deviations. Can you say more about like obviously you could just go weight the different deviations. You can just easily go do that. Nothing really in the algorithm needs to change, but maybe you could help understand where would that weighting come from? Why would we pick one over the other? Is there some natural choice we should be making?
Sure. So it kind of comes down to the fact that a more complicated deviation type has many more of these regrets that we need to keep track of, and that gives us some kind of gives us a notion of simplicity, separating these different deviation types. So you might have Like, for example, if you use EFR with the tips deviations, you're going to have a bunch of these regrets at a given information set to keep track of. But if you would have chosen the counterfactual deviations, you would only have a small set of those, right? And so when you use the tips deviations, your the emphasis that you have on competing with the counterfactual deviations gets swamped by just the sheer number of the other deviations you're now considering. So if you want to make sure that you perform at least as well as the counterfactual deviations, but you also still want to consider, at least in some lesser way, with the rest of the tips deviations, you now have to worry about reweighting the counterfactual deviations so that they don't get swamped by the sheer number of the other deviations. So perhaps a weighting that depends on like the relative size of different sets of deviations that have markedly different complexities would give you performance that will be that you can guarantee will always be at least as good as if you had only looked at, say, the counterfactual deviations. So maybe that would be able to avoid cases like this in Goof's three-player Goofspiel, where CFR actually does a little bit better than tips. And I'm thinking about so
are you thinking you would do something like tips deviations, there's n squared or number of actions squared more of those. So you would just actually weight the counterfactual ones by number of actions squared more? Like, is that kind of where you're thinking a weighting might come from?
Yeah, exactly. Something like that, perhaps. What I'm maybe a little bit more interested in is not to set that to some fixed weight, but maybe just learn it. So you could have a learning algorithm that's kind of selecting which deviations actually look good and which ones look worse, so that you're kind of selecting an ensemble of a restricted ensemble of deviations rather than just the one that's given to you. But yeah, both of these, kind of either the fixed or the learning method, might both be useful.
Okay, thanks.
Yeah, thank you. Sorry, Revan has a comment. Do you have any early results intuition for when stronger deviation types might be much more preferable for a given game? Yeah, so that's hard to say. So we actually have some examples in our the paper before this at AAAI called Hindsight Rationality of Hindsight and Sequential Rationality of Correlated Play, where we give some really simple examples about where particular deviation types will do well and where other ones will fail. So it kind of depends on where the value from the game is coming from. So for example, if the value in the game is coming from decisions at the beginning, near the beginning of the game, and you're able to learn those really well, essentially coordinating with the other players at the beginning of the game in order to get a lot of value, then you're going to want to have a deviation type that is like the causal deviations, where you get to and these are deviations that are unlike the counterfactual deviations. You need something different that's going to let you kind of correlate your behavior later in the game with behavior at the beginning of the game. Conversely, the counterfactual deviations do well when correlation at the end of the game is what's getting you value. So there's kind of this temporal dependence of where value is coming from. It's almost like a credit assignment problem that you need to think about. I mean, related to this is this idea of ensuring, having a big set of deviations to keep track of, but then weighting them so that you make sure that you're not going to do too poorly with respect to some smaller set of deviations. So that would at least alleviate, one problem. Yeah, it's unclear right now when you really need stronger deviation types. I think it does tend to help more in multiplayer and general sum games. So you can see here that the gaps between CFR and the other algorithms are maybe small, but you can get bigger gaps in general sum games between different deviation types. So that would be my first recommendation, is just you need stronger ones in general sum multiplayer games for sure. Yeah, thank you.
Okay, if there's no other questions, we're coming up on 1 o'clock, so I think we'll wrap things up. Thank you again, Dustin, for presenting on this long weekend Friday. And thanks everyone for coming. And we will see you again next week. Have a great long weekend, everyone.
Yeah, thanks everyone. Thanks for inviting me.